Hello everyone. So this next lab is called the basic capacitor, and you're going to do a couple of experiments with a simple capacitor, essentially measuring capacitance as a function of the distance between the capacitor plates. So capacitor is essentially two conducting plates with some distance between them. That distance can be separated by air or some other insulating material, depending on how large the capacitance has to be. But when you hook this up to a power supply, like a battery or something, so you put a voltage between the two plates of the basic capacitor, you get charge on the plates. There's positive charge on the plate connected to the positive pole on the voltage source, and then the same amount of negative charge on the plate connected to the negative pole. And the amount of charge is given by this equation. So, not surprisingly, the amount of charge is proportional to the voltage that you put between there. The higher the voltage, the more charge you have on the plate. It's also proportional to the area of one of the plates. That's just the surface area of one of these plates. The bigger the plate, the more charge it's going to hold at a given voltage. What may not seem so obvious is that the amount of charge is inversely proportional to the distance between the plates. The closer the plates are together, the more charge will build on the capacitor for a given voltage. And you can sort of see why that is when you think about the positive charge on one side and the negative charge on the other side. They'll attract each other by the Coulomb force, and so they sort of help each other get onto the plate. So anyway, this is how much charge will form on a plate. The epsilon naught, of course, is the permittivity of free space. It's a constant, 8.854 times 10 to the minus 12 farads per meter. Now, why do you do this? Why do you build capacitors? Why do you build these devices to hold the charge when you apply a voltage? Well, there's many different kinds of capacitors. Here's a bunch of different types of capacitors, and they're used for a bunch of different purposes. Probably the most common, well, definitely the most common capacitor is a microscopic capacitor used in solid-state memory, like the memory inside your computer or on a SD card or some other sort of solid-state memory where there's no moving parts. So you can see in here, every one of these little rigs holds a bit of information, a 1 or a 0. And there's a capacitor in it, and there's a transistor in it. A transistor is like a solid-state electrical switch. And when the capacitor is charged, that's a 1 or a 0. I don't know exactly how they do it, but it's either charged or uncharged, signifying whether that's supposed to be a 1 or a 0 in the data set of bits. Now, when you think about it, a gigabyte hard drive has 8 gigabits of data, so there's 8 billion of these capacitor transistor pairs in there. So you own literally trillions of microscopic capacitors. So that is, there's more capacitors doing that than anything else in the world. So they hold charge in order to indicate the presence of a 1 as opposed to a 0. This is called a variable capacitor because you can vary the capacitance. These plates right here can dovetail between these plates down here, changing the capacitance of the plates. It's like varying d, the distance between the plates. And this used to be used, probably still is used, to tune old radios. So the antenna circuit in an old radio had a variable capacitor in it, and that would change the frequency that the antenna would be sensitive to. So here's a variable capacitor. Here's a couple of capacitors on an electronic circuit board. I don't know what the specific function of these are, but there's loads and loads of these in electronic circuitry. Now here's another application. These three items together. This is the device that produces microwaves in a microwave oven. This is a big transformer that transforms the 120 volt AC electric current that comes out of your wall socket into about something like 4,500 volt AC. And the capacitor is part of the system to turn the AC into DC. Alternating current goes back and forth. DC goes in one direction. So the capacitor is designed to turn the AC into DC, or it's part of a system that does that, because the magnetron, the thing that produces the microwaves, requires DC electricity at a high voltage to produce microwaves. So there's one of these great big capacitors in every microwave oven. Here's some even larger capacitors. These are at some sort of a electrical substation, the place where they transform electricity to send it out to neighborhoods, transform it to a lower voltage than is transmitted over long distances. And their function in here is the AC voltage and current can get out of sync in electrical distribution grids, and capacitors are used to get them back in sync. This is a relatively newer kind of capacitor. They call this an ultra capacitor because they have very large capacitance, 3,000 farads of capacitance. So this can hold a whole bunch of charge and, in fact, considerable energy. Capacitors are usually not used to power things like motors or whatever, but if they have very large capacitance, they can actually be used to store energy. And this may be very important in the future. For instance, in vehicles, this is a Formula E race car, runs on electricity, and one of the things that these do is when they're going real fast, when they approach a corner, instead of hitting the brakes to turn that kinetic energy into heat, they charge capacitors with electricity, with the kinetic energy is turned into electrical power and stored momentarily, and then when they come out of the corner, they can reuse the energy to speed back up. Capacitors can act like batteries. They don't hold as much energy, but the advantage is they can charge and discharge faster than batteries can, and so they can be used for situations like this. Okay, so it's this relationship that we'll be testing. It's specifically the dependence of the capacitance on distance d. So here's the relationship between the charge on a capacitor and those three factors: the voltage, the area of the plate, and the distance between them. Now, in most capacitors, A and D don't change, right? So epsilon naught A over D is a constant, and that constant is called the capacitance of the capacitor. For most capacitors, that doesn't change, so they just quantify the capacitance in terms of that. Epsilon naught is a constant, right? So that doesn't change either. So this capacitance is dependent on D, and you can write it like this. The capacitance is epsilon naught A times 1 over D, which means the capacitance is proportional to the inverse of the distance between them. What you're going to do in this exercise is you're going to use this simulated capacitor, vary the distance between them, and for a bunch of distances measure the capacitance. And then what you'll do is you'll make a plot with Microsoft Excel or on paper, where you'll plot for all these distances, you'll plot capacitance measured as a function of 1 over D. So you take all the distances, take the inverse, you'll plot C as a function of 1 over D. The reason you're going to do that is because since this relationship holds, since C is proportional to 1 over D, that should be a straight line. And the slope of the straight line is going to be epsilon naught A, right? So you're going to find the slope of that straight line and divide by A to find the epsilon naught, the permeability of free space. So so that's how this is going to work. And here's just a screenshot of this simulated capacitor you're going to use. This little green arrow, up and down arrow, if you move that up and down, you can actually vary the distance between the capacitors. You can also vary the area by moving that other green right and left arrow there. There's a couple of questions that has you move that arrow, but then you're going to leave that alone and move the distance and measure capacitance, and then plot this plot and find the slope of it, and from that find epsilon naught. Okay, and once again, if you're uncomfortable using Microsoft Excel to make a XY plot, or if you're uncomfortable finding the slope from that plot, just contact me and I'll walk you through that. So that's basically how this thing's going to work.